In this video, we demonstrate the Imagine system for disassembly tasks with a hard disk drive as a representative electromechanical device. The Imagine system autonomously analyzes the current scene, detects affordances, decides the next disassembly actions, and executes the parameterized actions on the real robot. The simulation is requested by the planner to reduce the uncertainty of the next decision. The system can also replan the action in case of failure and adapt the decision-making to the new scene. First of all, the state estimation component captures the scene using an RGB camera from the top and runs screw detection and classification. Here, one screw of type TOX8 is detected on the lid, and the ASC detects the unscrewable affordance as visualized on the point cloud. And then the planner decides to switch to the screwdriver for the unscrew action. The robot calibrates the screwdriver using a tool-mounted camera as shown on the top right corner, and then uses the visual sovereign controller to insert the tool tip into the screw. However, due to accumulated error in the whole system, the unscrew action might fail since it requires the sub-millimeter accuracy. This leads to no effect of the shake away action. Our system can recognize the failure case and replan based on the new scene analysis. The system decides to continue the process with another unscrew action. Under the new scene, a screw of the same type as the previous one is detected on the platter, so the equipped screwdriver on the robot can be used for this unscrew action. Without screws in the scene, the state estimation performs wire detection and component segmentation. Here, we visualize the 3D outlines of each detected part in the scene on the point cloud, as well as the affordances detected by ASC. The precedence diagram represents an abstraction made by the planner of an observation directly extracted from perception. This indicates that the magnet and the spindle hub are not preceded by other parts and can be removed first. The diagram below shows the probability of success of each action, which shows no viable action for the spindle hub and two viable but ambiguous actions for the magnet. They are lever and shake away actions. Thus, a simulated action is requested to disambiguate between the two. Since the simulated lever action is successful, the system decides to switch to the lever tool and then lever the magnet. The lever motion is learned from human demonstration by the robot-assisted kinesthetic teaching, and the lever pose is parameterized by the ASC according to the position of the magnet in the scene. In this new scene, the read-write head is occluding the platter and the bottom magnet, so the planner sees it as the only viable parts to target, and shaking is the only available action for the read-write head. Since shaking doesn't take any effect, the planner assumes that there should be some hidden task on the bottom side and flips the device. In the next, unscrew actions are required to disassemble the PCB. With the PCB being removed, the hidden screws that hold the parts on the top side is finally visible. After the unscrew and shake action, all the parts on the bottom side except the bay are dismantled. However, the system remembers that the disassembly process on the top side is not complete and flips back to check whether any further disassembly actions are required or not. In this case, all parts inside the HDD are removed and the system resets the robot to prepare for a new disassembly task. In the next, we demonstrate the Imagine system for disassembly tasks with a GPU as an alternative device. The state estimator detects no screws, but a cable that connects the cooling unit to the main PCB board. This cable is visualized on the point cloud with a blue curve. The cardboard affordance is overlaid on the blue curve with green beans. The planner decides to use the rotating cutting tool to cut the wire. On the top side, no viable actions is found anymore. The system flips the device. On the bottom side, one Phillips screw is found and the system switches the corresponding screwdriver to remove this screw. The robot fails the first unscrew attempt. The planner gives the suggestion to repeat it. The planner attempts to remove the PCB because PCB is a part that is typically removed in other devices. However, in the current scene, the PCB is actually the backbone that cannot be removed by the planned suck action. More work is needed for recognizing which is the backbone part of a device. Since the suck action takes no effect, and no further disassembly actions are viable, the system resets the robot for the next disassembly task. Finally, we show 6 different disassembly trials in one view. Thanks for watching.